Why haven't we found intelligent life yet? In the early 2000s, a team of researchers at the Parkes Observatory, Australia, started detecting a series of bizarre millisecond-long radio bursts. They called them peritons. Strangely, they had many characteristics in common with fast radio bursts, a mysterious class of phenomena believed to originate from deep space. Speculation about peritons was inevitable. Newspaper articles even claimed that these puzzling signals could be attempts at communication by an alien civilization trying to reach out to us across the cosmos. But the Parkes team wasn't convinced. Soon enough, they realized the periton signals weren't coming from space at all. They were coming from microwave ovens within the observatory itself. As is so often the case, our hopes of discovering intelligent extraterrestrial life turned out to be a false alarm. So is there really anything or anyone out there? Are we truly alone in the universe? And if not, why haven't we found intelligent life yet? 14.6 billion years ago, the universe suddenly exploded into existence. From the center of the Big Bang came an outpouring of galaxies. In our own galaxy, the Milky Way, astronomers estimate that there could be as many as 400 billion stars, many of which have planets orbiting them, just as they do in our own solar system. Like all planets orbiting our sun, barring our own, most of them are uninhabitable. But what about the planets in other parts of the galaxy? Assuming the Earth's conditions have allowed complex intelligent life forms to develop, it follows that other planets with similar conditions should also be capable of sustaining complex life. If there are 400 billion stars in our galaxy, even if only half of them have been orbiting planets, and just one of those planets has a solid surface and orbits in the Goldilocks zone, we can expect there to be at least 200 billion potentially habitable planets in the Milky Way. So why haven't we found them yet? Despite decades of searching, we haven't found any concrete evidence that we are not alone in the universe. This has become known as the Fermi paradox, named for the physicist Enrico Fermi. The paradox highlights the statistical discrepancy between the high probability of intelligent life evolving on various planets around the galaxy and our total lack of evidence that such life exists. Fermi noticed this paradox back in 1950. And if the lack of evidence for intelligent life was noticeable then, the great silence of the universe has only grown more deafening in the 7 decades since. Our planet orbits the sun in what is known as the habitable or Goldilocks zone. It's far enough away from the sun to not be too hot, but not so far away that it's too cold. In other words, it's just right. However, many scientists, including Enrico Fermi, have pointed out that Earth seems to be a pretty typical planet. It has a typical rocky surface, and it's located in a fairly standard solar system in an unexciting part of a common barred spiral galaxy. This principle of mediocrity, coupled with the estimated number of planets that sit in the Goldilocks zone of their solar systems, inspired the idea that life should be common throughout the universe. Not only that, but since such an apparently mediocre planet gave rise to intelligent life forms like humans, it seems reasonable to assume that other Earth-like planets should be capable of doing the same thing. But as Fermi said back in 1950, where is everybody? One of the leading explanations for the Fermi paradox is the rare Earth hypothesis. It asks the question, what if, rather than being commonplace, Earth is actually exceedingly rare? According to Peter Ward and Donald E. Brownlee, the scientists who came up with the hypothesis, there's more to our planet than just having a rocky surface and orbiting the sun in the Goldilocks zone. In the past few decades, astronomers have identified a number of worlds both within our solar system and in other star systems that are very similar to Earth and may contain evidence of life. Mars, for instance, is now cold and bone dry. but evidence suggests that the red planet once had flowing water, a thicker atmosphere, and a warmer climate. Europa, one of Jupiter's many moons, meanwhile, has plenty of surface water. Although it's cold, with temperatures dropping to 160 degrees C at the equator and minus 220 degrees C at the poles, Europa's oceans are prevented from freezing by tidal heating. Outside our solar system, scientists have discovered planets like Proxima Centauri b, Kepler 186f, and Kepler 452b, and 3 planets from the TRAPPIST-1 system. All are in the habitable zones of their systems. Yet we haven't detected any signs of life on or around any of these extrasolar worlds. So, what if Earth really is unique? What does Earth have that these other planets lack? When studying potential habitable planets or moons, scientists look for certain features, such as an atmosphere with life-supporting gases in it and a tidal system to keep global oceans moving. But one of the most important of these features is plate tectonics. Plate tectonics have had a profound influence on the history of our planet and may even have played an important part in the origins of life itself. On Earth, the movement of the planetary crust is driven by internal heat, with convection currents in the molten mantle slowly shifting the rocky plates above. These movements create dynamic geological activity, including earthquakes, volcanic eruptions, and the formation of entire mountain ranges. Although the plate tectonics are certainly capable of wreaking havoc and causing intense damage, scientists believe it is precisely this feature of our planet that allowed it to become a haven for billions of life forms. Volcanically active regions, particularly along mid-ocean ridges and hydrothermal vents, provide energy-rich environments that could have fostered the complex chemistry for the first life forms to emerge, a process known as abiogenesis. This was the origin of life from non-living matter. Chemical molecules gradually become self-replicating biological cells. It was an extraordinary transformation, and while some think abiogenesis is inevitable under the right conditions, many scientists have pointed out the unlikelihood of it ever happening. Without plate tectonics, which created hydrothermal vents, it is possible that abiogenesis never would have taken place on our planet, and life would never have begun. Crucially, all of the potential habitable worlds we have been able to study are mostly tectonically inactive. Only Europa has been discovered to have possible plate tectonics, but more research is needed to confirm if this is the case or not. Enrico Fermi and many other scientists assumed that if the complex life could have evolved on a mediocre planet, what's to stop it happening again or having already happened before? But given what we know about plate tectonics and its apparent scarcity in the other planets we have been able to study, can we really consider Earth to be anything other than atypical? Even if Earth turns out to be just one of many worlds in the galaxy with active plate tectonics, can we assume that abiogenesis would naturally take place on those worlds as well? Ask a group of scientists who study evolution and the origins of life, and many will tell you just how improbable the whole process really was. For life to begin, a number of highly specific and independent events had to occur. There had to be a source of energy, a supply of organic molecules, and a setting in which those molecules can be concentrated and arranged into complex polymers. Then these needed to somehow come together in just the right way to create a system capable of both metabolism and replication. This is a huge and complicated leap. Even on Earth, where all the right ingredients appear to have been present, it took hundreds of millions of years for the first true cells to appear. And even if life does begin, that's just the first hurdle. For the vast majority of Earth's history, life remained astonishingly simple. For over 3 billion years, our planet was dominated by bacteria and archaea, single-celled organisms with no nucleus and no overly complex structures. So, how did we go from a planet populated by only single cells to one ruled by intelligent space-faring apes? Multicellularity requires a suite of highly specific innovations. First, cells must be able to stick together in a stable way rather than just forming a chaotic cluster. Then, they must learn to communicate with each other through chemicals so that they can coordinate their activity. Crucially, some individual cells must give up their own reproductive potential for the benefit of the whole organism. This led to the specialization of cells for different things like our nerve, brain, or skin cells. It also took a staggeringly long time. The earliest known multicellular organisms don't appear in the fossil record until the Ediacaran period around 600 million years ago. That's more than 3 billion years after life began. Even with the right conditions, multicellularity has evolved only a relatively low number of times on Earth. And true complexity, the kind seen in animals, plants, algae, and fungi, has evolved in only those 4 groups. Many lineages of multicellular life stalled at the level of simple colonies or filaments. Only in rare cases did they cross the threshold into true differentiation and tissue specialization. So just as a biogenesis may be an exceedingly rare event in the universe, so too might be the rise of complex multicellular life. A planet might well harbor oceans teeming with single-celled organisms for billions of years, without ever producing anything more elaborate than microbial mats. That kind of biosphere could easily go undetected by our current instruments, making the universe appear silent and lifeless, even if microbial life turns out to be relatively common. It's possible that our planet represents not just a rare oasis of life, but a near-unique site of evolutionary complexity. And if that's true, then the silence we hear when we scan the stars may not be mysterious at all. It may simply be the sound of an empty or largely microbial cosmos. However unlikely the evolution of intelligent life on our planet was, or how rare Earth may be, that doesn't necessarily mean that intelligent life cannot possibly exist elsewhere in the universe. The zoo hypothesis offers a compelling explanation for our total lack of contact with alien life. It suggests that life can and does exist outside Earth, and that there are millions of extraterrestrial civilizations in existence. In fact, it has been argued that if extraterrestrial intelligence did exist, the alien civilizations would have created self-replicating machines that would travel through the cosmos. John von Neumann first envisioned these machines as the most effective way of performing resource extraction activities such as mining in space. In theory, these machines would be able to use some of the resources they extracted to replicate themselves. Given the age of the universe and that scientists think we are not far off from making our own self-replicating machines, such machines would already be common throughout space. We should in theory have already encountered them, but we haven't since it took 4.6 billion years after our planet formed for modern humans to emerge. And it has only been within the last century that we have begun our first foray into space. Uncountable extraterrestrial civilizations could have risen and fallen during that time. Assuming that this is true, these civilizations would be far more advanced than we are. They could have technology sophisticated enough to completely hide their existence from us, silently observing us without alerting us to their presence. Maybe that's why we haven't come across any self-replicating machines. But why would alien civilizations do this? In the TV series Star Trek, the crew of the Enterprise regularly come into contact with alien civilizations on distant planets. However, they are not allowed to meddle with civilizations deemed to be less technologically advanced than they are, known as the Prime Directive. The rule allows the crew to observe and study the aliens, but they cannot interfere. This is all science fiction, of course, but could something like this really happen? According to the zoo hypothesis, it's possible, except in this scenario. The roles are reversed. We are the technologically inferior civilization being quietly observed by aliens many times more advanced than us. This hypothesis explains the Fermi paradox by arguing that intelligent life does exist throughout the universe. It's just hiding. Like in Star Trek, technologically advanced aliens could be deliberately avoiding communication with Earth to allow natural evolution and socio-cultural development to take place. Some even suggest that when humanity has reached a certain technological or cultural threshold, intelligent extraterrestrial life may reveal itself to us, believing the human species to be ready to deal with such a momentous occasion. If this is the case, we have to assume that intelligent life is inherently altruistic. The zoo hypothesis calls to mind an image of a birdwatcher concealed within a wildlife hut, silently watching and not interfering. But what if intelligent life has another darker reason to hide from us? In 2008, Chinese author Liu Cixin published a science fiction novel titled The Dark Forest. In the novel, Earth is threatened with invasion by an alien civilization from the Tricolaris system. Central to the plot of the book is that any civilization that broadcasts its existence to the universe will almost certainly invite its destruction by another civilization. According to the Dark Forest hypothesis, which was named after Log, the intentions of a newly contacted civilization can never be known with any certainty. So if one is encountered, extraterrestrials may deem it best to shoot first and ask questions later. This way they avoid the potential destruction of their own civilization. Like nations with nuclear weaponry, civilizations capable of space travel have the technological ability to destroy other civilizations. But by possessing such weapons, they are viewed as potential threats by their interplanetary neighbors. As such, the universe is like a dark forest that is filled with armed hunters, creeping silently through the shadows. Each hunter is keenly aware that the forest around them is filled with danger, and that they are also being hunted. So if the universe is like a dark forest and intelligent life hides itself away in case of destruction, that would explain why we have not encountered any evidence of extraterrestrial civilizations yet. However, it also suggests that if we continue broadcasting our location throughout the galaxy in our search for alien life, we may be putting ourselves in immense danger. As terrifying as the dark forest hypothesis is, there is one final, even more horrifying theory to explain the Fermi paradox. According to the astronomer Nikolai Kardashev, there are 3 different types of civilizations. Type 1 is able to access all the energy available on its planet and store it for consumption. Type 2 can directly harness energy from the sun, most likely through the use of a Dyson sphere. Type 3 is able to capture the energy emitted by its galaxy and all the objects in it, such as every star, every planet, and every black hole. Since humanity has not yet been able to access and use all the energy available to us on our planet, we have not reached Type 1, but we're close to it. The Great Filter hypothesis asks the question, what if there is a barrier to the development of intelligent life somewhere along the Kardashev scale? Since we haven't come across any alien civilizations, be they Type 1, 2, or 3, extraterrestrial intelligence may in fact be exceedingly rare. Robert Hansen, who popularized the hypothesis, argues that the appearance of advanced intelligence is probable, but there is a great filter which acts to reduce the number of places in the universe where intelligent life might arise. Currently, we are only aware of the existence of one intelligent civilization, our own. This filter could lie in our past, meaning we've already overcome it, or it could be in our future. So, where might the Great Filter be? The hypothesis proposes a step-by-step process to intelligent life. Considering the apparent rarity of life in the universe, let alone intelligent life, one step in the process must be improbable. According to Hansen, there are 9 steps in the process. First, there needs to be the right star system, which includes organic materials and potentially habitable planets. Second, reproductive molecules like RNA need to exist. Third and fourth, single-celled prokaryotes and eukaryotes need to evolve. Fifth, life must begin sexually reproducing itself. Sixth, multicellular life must evolve. And seventh, intelligent creatures who use tools must emerge. We have successfully passed these 7 steps on Earth and are currently at the 8th step, a civilization advancing toward the potential for colonizing space. The 9th step, an explosion of interstellar colonization, is in our future. But what if this step is where the filter lies? If the 8 steps we have already completed were not improbable, we might assume that many extraterrestrial civilizations at a level of technological sophistication similar to our own would exist. However, the Great Filter hypothesis points out that none appear to have made it to step 9, or the universe would be full of extraterrestrial colonies. Robert Hansen thinks that step 9 is the improbable step in the process. But given humanity's current rate of technological advancement, the only thing that appears likely to keep us from step 9 is some sort of catastrophe. Many scientists think it could be the complete depletion of resources on Earth. Or perhaps extreme climate change could make our planet inhospitable for humans and most other life. Still, others have suggested that a massive pandemic, one much worse than CO-19, could devastate our species to an extent that human civilization collapses. Another unsettling prospect is World War II, in which nuclear weapons could totally destroy the planet. This is why the Great Filter hypothesis is so disturbing. It proposes that civilizations cannot move past the 9th step in the process. The most commonly cited reason for this is that civilizations inevitably destroy themselves once they reach a certain point. This point could potentially be type 1 on the Kardashev scale. And if this is true, our future could be very bleak. To counteract the horror of the Great Filter and the Dark Forest, the sustainability solution offers a more hopeful explanation to the Fermi paradox. In the 21st century, a major concern for almost all governments, businesses, manufacturers, and individuals is sustainability. We are constantly bombarded by calls to action to reduce our plastic consumption and donate to tree planting initiatives. But what if sustainability is a concern not just in our planet, but across the whole universe? The sustainability solution first proposed by Jacob Hackmesera and Seth Bow in 2009 suggests just that. The Fermi paradox, as convincing as it is, makes a lot of assumptions about what extraterrestrial civilizations will be like. Hackmesera and Bow point out that the paradox assumes that intelligent life will always expand out from its home planet to colonize the galaxy, obviously based on the behavior of human civilizations. But Hackmesera and Bow argue that this kind of territorial expansion is almost always unsustainable. As we have seen on our own planet, we are coming dangerously close to running out of several finite resources like oil and gas. Once these resources are gone, our expansion into space must either end or become more sustainable. Another observation they make is that many human populations, such as indigenous hunter-gatherers, live sustainably. There's no question of their intelligence, and yet their ways of life would be undetectable from space. According to the sustainability solution, since human populations are gradually transitioning towards a slower growth, more sustainable development pattern, it is possible that alien civilizations are doing the same thing. Imagine a spacefaring extraterrestrial species that traveled through the galaxy in ships made entirely of natural materials. There could be no doubt of their technological sophistication or intelligence, but their activities might go wholly undetected by even our most advanced instruments. Some intelligent alien civilizations might have begun their transition to more sustainable development earlier in their history, which could have caused their technological and population growth to become slower and less damaging to their planet. As a result, these civilizations may lack spacefaring technology, but could still be very active and innovative on their home planet. This could explain why we haven't found evidence of intelligent life yet. It could be out there. It's just harder to detect. No matter how convincing or unsettling some of the explanation for the Fermi paradox are, we have to admit that there are limitations to our search for intelligent life beyond our planet. For one, despite our enthusiasm, we have only been looking for a few decades. For most of that time, we have relied on radio telescopes to scan the skies for potential alien signals. but even our own most powerful instruments can only detect a narrow band of signals across a relatively small region of the galaxy. If alien civilizations are broadcasting in a way we haven't yet anticipated, or if they are using technologies beyond our current understanding, we would have no way of hearing them. Even the ambitious SETI program is limited by budget, infrastructure, and sheer scale. The vastness of the universe presents an almost unimaginable challenge. It's like dipping a glass into the ocean and wondering why you haven't caught any fish. That said, our capabilities are improving all the time. As time goes on, we will inevitably make breakthrough discoveries, and one of these could be extraterrestrial life. Just in the last decade, we've already discovered thousands of exoplanets using missions like Kepler and TESS, many of which lie within their stars' habitable zones. In 2017, scientists confirmed the existence of the TRAPPIST-1 system, home to at least 3 Earth-sized planets that may be capable of supporting life in water. We have even begun developing methods to detect biosignatures, chemical markers like methane, oxygen, or complex organic compounds in alien atmospheres that could hint at biological activity. We are also starting to search for technosignatures. These are indicators of advanced technology such as laser pulses, radio bursts, artificial light, or waste heat from megastructures like Dyson spheres. Technosignatures are therefore like the fingerprints that an extraterrestrial civilization might inadvertently leave behind. Already, scientists have made several intriguing discoveries. Back in 1977, astronomer Jerry Emin was scanning the sky using the Big Ear radio telescope at Ohio State University when he spotted something extraordinary: a sudden, strong narrowband radio signal that lasted for just 72 seconds. Emin was so astonished he circled the readout and wrote a single word in the margin: "Wow." To this day, the so-called WOW signal remains unexplained. It came from the direction of the constellation Sagittarius and matched the expected signature of an artificial transmission, but it has never been detected again. More recently, in 2017, astronomers in Hawaii detected a strange object passing through our solar system. They named it Oumuamua, meaning first distant messenger, because it came from beyond our system. More recently, in 2017, astronomers in Hawaii detected a strange object passing through our solar system. They named it Oumuamua, meaning first distant messenger, because it came from beyond our system. Considering its relatively small size, between 100 and 1,000 m long and between 35 and 167 m thick, it was originally thought to be a comet, but it showed no signs of having a coma, the usual nebula of gases that surround comets when they pass near the sun. And it's moving fast. In fact, by the time it was detected, it was already on its way out of the solar system. Considering its relatively small size, between 100 and 1,000 m long and between 35 and 167 m thick, it was originally thought to be a comet, but it showed no signs of having a coma, the usual nebula of gases that surround comets when they pass near the sun. And it's moving fast. In fact, by the time it was detected, it was already on its way out of the solar system. This makes studying it difficult because it's already so far away, but even in such a short time frame, scientists have been able to observe several intriguing details. It is uncommonly cylindrical in shape, and it moves through space in a seemingly unnatural way. Rather than spinning around a principal axis, as most objects in space do, it appears to be tumbling. Some suggest that it could have collided with something, which may explain its strange tumbling motion, but it's impossible to say without further study. This makes studying it difficult because it's already so far away. But even in such a short time frame, scientists have been able to observe several intriguing details. It is uncommonly cylindrical in shape, and it moves through space in a seemingly unnatural way. Rather than spinning around a principal axis, as most objects in space do, it appears to be tumbling. Some suggest that it could have collided with something, which may explain its strange tumbling motion, but it's impossible to say without further study. Most intriguing of all, as Oumuamua passed by the sun on its way out of the solar system, it sped up. This is to be expected from comets which experience outgassing, whereby volatile substances inside the comet evaporate as the sun heats its surface. But Oumuamua has no such tail of gases, which begs the question, what made it accelerate? Could it be an engine of some kind? Most intriguing of all, as Oumuamua passed by the Sun on its way out of the solar system, it sped up. This is to be expected from comets which experience outgassing, whereby volatile substances inside the comet evaporate as the Sun heats its surface. But Oumuamua has no such tail of gases, which begs the question, what made it accelerate? Could it be an engine of some kind? Although some scientists have attempted to explain this mysterious acceleration, such as suggesting that Oumuamua's gases were invisible, the jury is still out on whether it is just another comet or if it was crafted by an alien civilization. Even if it turns out to be just another comet and nothing to do with extraterrestrial life, Oumuamua is definitely worth studying. And scientists are already working on probes such as Project Lyra to catch up with it. Although some scientists have attempted to explain this mysterious acceleration, such as suggesting that Oumuamua's gases were invisible, the jury is still out on whether it is just another comet or if it was crafted by an alien civilization. Even if it turns out to be just another comet and nothing to do with extraterrestrial life, Oumuamua is definitely worth studying, and scientists are already working on probes such as Project Lyra to catch up with it. So far, our encounters with interstellar objects are limited to just Oumuamua, but our ability to find and study potential habitable planets is increasing. With advanced technology like the Kepler Space Telescope, we can look far beyond our own solar system to make discoveries hundreds of light years away. In 2015, the telescope was used to discover K218b, an Earth-like planet orbiting the red dwarf star K218. It's located in the habitable zone of its star system. So far, our encounters with interstellar objects are limited to just Oumuamua, but our ability to find and study potential habitable planets is increasing. With advanced technology like the Kepler Space Telescope, we can look far beyond our own solar system to make discoveries hundreds of light years away. In 2015, the telescope was used to discover K218b, an Earth-like planet orbiting the red dwarf star K218. It's located in the habitable zone of its star system, and in 2019, scientists reported the presence of water vapor in K218b's atmosphere. Some have even suggested that the planet could have oceans, and if that's true, it's easy to imagine that life might thrive within them. And in 2019, scientists reported the presence of water vapor in K218b's atmosphere. Some have even suggested that the planet could have oceans, and if that's true, it's easy to imagine that life might thrive within them. Apart from water vapor, K218b's atmosphere also contains small amounts of carbon dioxide and methane, but it's mostly made up of hydrogen. Obviously, this is very different from Earth's nitrogen and oxygen-rich atmosphere, which contains minimal hydrogen. However, studies on Earth have known that certain microorganisms can live in hydrogen-rich atmospheres. So although we humans wouldn't survive on K218b, other forms of life could be quite comfortable. Apart from water vapor, K218b's atmosphere also contains small amounts of carbon dioxide and methane, but it's mostly made up of hydrogen. Obviously, this is very different from Earth's nitrogen and oxygen-rich atmosphere, which contains minimal hydrogen. However, studies on Earth have known that certain microorganisms can live in hydrogen-rich atmospheres. So although we humans wouldn't survive on K218b, other forms of life could be quite comfortable. But perhaps the most exciting news from K218b came in 2025 when scientists reported the possible presence of dimethyl sulfide or DMS in the planet's atmosphere. On Earth, most of the DMS in our air is produced by marine phytoplankton, and on K218b, the concentration of DMS have been claimed to be up to 20 times higher than on Earth. But perhaps the most exciting news from K218b came in 2025 when scientists reported the possible presence of dimethyl sulfide or DMS in the planet's atmosphere. On Earth, most of the DMS in our air is produced by marine phytoplankton, and on K218b, the concentration of DMS have been claimed to be up to 20 times higher than on Earth. So, could microorganic life exist on K218b? We only have early speculative evidence right now, but it's an exciting prospect to consider. So, could microorganic life exist on K218b? We only have early speculative evidence right now, but it's an exciting prospect to consider. Today, our search for intelligent life is growing more and more sophisticated. One of the most ambitious projects is the breakthrough LISTEN. This project is using some of the world's largest telescopes to scan the skies for technosignatures. Unlike earlier efforts, the Breakthrough Listen incorporates the power of AI and machine learning, which can sift through vast quantities of data with far greater efficiency than human researchers. The aim is to spot patterns, anomalies, or bursts of energy that might otherwise go unnoticed, potentially uncovering signs of intelligent life that might otherwise have been buried by the noise of the cosmos. For now, we still don't have any conclusive evidence of intelligent life beyond our solar system, but with the rate at which technology is improving, it might just be a matter of time before we finally find a signal or curious object that proves to be of extraterrestrial origin. Are we truly alone, or are we just not listening the right way? Let us know your take in the comments below, and subscribe to keep exploring the most fascinating questions of the universe with us. Are we truly alone, or are we just not listening the right way? Let us know your take in the comments below, and subscribe to keep exploring the most fascinating questions of the universe with us.